Assalamu alaikum warahmatullahi wabarakatuh. This is Dr. Ali El-Moursy. We are still in the Digital Logic Design DLD lectures, and now we are in lecture number 25, part 3, related to the analysis for synchronous sequential circuits. The last two lectures we gave simple circuits. Actually, we demonstrated the analysis steps through the well-known circuits called the JK flip-flop and D flip-flops. And today we will just take a very general example to demonstrate a more general case, which is the circuit that we have here. As you can see here, the circuit here is different from the circuit that we have demonstrated in the last two parts of the lecture in the regard of the number of pieces. Here I have two flip-flops instead of one. I have external input. I have a circuit, and introduced newly here is that this circuit, for the first time, we have an external output. Here is it. Okay. So as you can see here, in addition to the output going out from the flip-flops, as you can see here, we have also the output that is not directly connected to one of the flip-flops, which is the output Y, as you can see here. As you know, and as we mentioned before, okay, definitely here I have the output, which is in our analysis, the input. As you can see, the Q's of the flip-flops, the outputs of the flip-flops connected to the feedback. So accordingly, they are be considered as inputs in my analysis, as we mentioned before. So as Dr. Ali recommended before, the first thing to do is to do in-out analysis. Okay, so we need to identify the inputs, the outputs before we start working. So as we mentioned, we have what's called the state inputs. We have the external inputs. We have the state outputs. We have the external outputs. This is actually the table or the analysis that we used to do before we go and do the analysis for our circuit here. Agree? Now we need to have to be a little bit conservative of the space here. So now, can we identify the four different parameters here? State inputs. State inputs are the output of the flip-flops, which are connected to the feedback. By the way, the flow of signal coming from the input, as you can see here, going out from the combinational, going into the sequential, and coming from the feedback back to the system. And I have also output from here, supplies the output to the external output. And I have also signal coming from the input here, going to the flip-flop, and here going back through the feedback. This is the arrows, blue arrows here shows the flow of signal. Agree? Now we need to do the analysis. What kind of state inputs that you have? You have two flip-flops. That means you have two state inputs. I cannot call output of the flip-flops Q anymore because I have two. So I have to discriminate them. So for the sake of the analysis, I will call this flip-flop A, and this is flip-flop B. Accordingly, I have A and A bar as an output here, B and B bar as the output here. I have also D of A and D of B. Make sense? Everybody's following? Let me just a little bit make this clear. So I have DB, and this is actually flip-flop B. That means the output coming from here, which is connected to the input here. This is A, and here I have B bar, so this is B bar. Can you see this? Y also, it takes from the A bar and from the B. Now, forget the feedback completely. But before we do that, we need to continue this. So the state inputs here for the circuit are A and B. Similarly, I have what is the A of t plus 1 and B of t plus 1 as the state outputs. Okay? Right. External inputs, I have X. Right. External input output, I have Y. Make sense? Clear? After doing this analysis, I wanted to analyze this. So I have actually the circuit. I want to drive the equations as we did before. Put all combination on one side, put all sequential in the other side. Here I have part of the combinational is here, okay? So you can do analysis for that part as a part of the combinational. Let's analyze the combinational side right here. By the way, this is part of it. You can remove it here and put it here, but anyway, you don't have to do that. This you can do it as it is. This is combinational. This is actually till here. You have sequential, and you have part combinational here for the last part here. Okay, so it's part of the combination. This one. Right. For the combinational, can I identify the inputs? Inputs for the combinational are, what are the inputs for the combinational? Combinational has inputs X as an external. It has A and A bar, B and B bar. Outputs for the combinational are DA, DB, and Y. Can I drive equations for the outputs in terms of inputs? Yes. So the first equation here is Y equals to A bar or B. يبقى Y equals to A bar or B. Fine. DA, can I get an equation for DA? DA is an OR between X and A. DB equals to an AND between B bar hold a second. Something is missing here. Example is incomplete. Let me just verify my notes. Okay, so the example here is missing something. Let me just correct that. So I have another feedback coming from A bar here. Go to this state. Okay, so B equals to B bar, then ended with to an OR gate between an X bar ORed with an A. Agree? So I get an equation for DB, DA, and Y. So I am done with the combinational. Do I really need to do analysis for sequential? The answer is no. All what I need from the sequential is the characteristic equation. I have A of t plus 1 equals to dA. B of t plus 1 equal to dB. That's it. So now I'm ready for the state equations. I have three equations. Equation for y as it is. Y equals to A bar or B. A of t plus 1 equals to dA, which is x, or A. The last equation, the last state equation is for B of t plus 1 equals to dB, and dB is actually B bar, X bar, or A bar. So I am done with the state equations that we have just derived here. Those are the state equations. Three state equations for the three outputs of my circuit. And those state equations, you can see only the inputs. I have for total three inputs, A, B, X. I have total inputs, A of t plus 1, B of t plus 1, and Y. Three inputs and three outputs. These are equations of three inputs and the three outputs. Agree? Makes sense? Now, go to the next step. The next step or the next part that we want to drive is the table. Okay? So, the table here. So now I will build the table. I have inputs, I have outputs, and the inputs and outputs are two types. I have for the inputs, maybe the space will not allow me here. So let me just take some space here from this part. Let me take some space, okay? So here, we already know that I have external output, Y. Let me take some of this space. So we have here I have inputs, I have outputs, and the outputs are two parts. I have external and state. Agree? Now, I will have the following. And here also I have external and state. So, in the input side, I have what's called the present state, and I have external input. External input. I have here the next state, and I have external output. How many columns for the next state? Two columns. How many columns for the present state? Two columns. So for present state is represented by A and B, and the external is X. Agree? The outputs, I have A of t plus 1, B of t plus 1, and I have Y. Everybody's following? Now, I have here usually representing the states. States are represented here. Now I have a TT. TT for three inputs and three outputs. Can I build this TT? That means this TT has how many rows? Has 8 rows. So let me split this into two halves. These are another 2 halves, and finally I have to split those quarters as well. Agree? Make sense? Make sense? Okay. Now, can I fill in this CT? Yes. How? Input side, these are inputs. Okay, so this is actually the part 3, the state table. As Dr. I recommend, put the present state in the external, present next state in the external. The inputs are 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1. We did this 100 times from the beginning of this semester. Right. What about the outputs? We already have their equations. So let us and deal with each one. I have a of t plus 1. A of t plus 1 is O between x and a. Simply O between x and a. This is a, this is x, so OR them to get a is t plus 1. 0 or 0 is 0. 0 or 1 is 1. 0 is 0, 0. 0, 0 is 1. Then I have here 1, 1, 1, 1. It's an ORing. Make sense? Any question? Next, b of t plus 1. B of t plus 1 is actually ending between b bar or with a x bar or a bar. If b equals to 0, b, or let's start by a. When a equals to 0, when a equals to 0 means this x or x bar or 1. X bar or 1 means 1. That means the equation will be simply b. The equation simply b bar if a equals to 0. A 0 equation is b bar. Means 1, 1, 0, 0. Agree? When a equals to 1, if a equals to 1, that means it is b bar x bar. B bar x bar means it is b bar ended مع الاكس بار means 1 ended مع الاكس بار اللي هي 1 هتبقى 1 1 ended with 0 هتبقى 0 0 ended with 1 will be 0 sorry it is when a is 1, that means b bar x bar. This is b bar, this is b bar. B bar means 1 and it is x bar. 1 x bar about this is so it is simply it is b bar x bar. That means when b equals to b equals to 0, it is x bar. When b equals to 0, it is x bar. When b equals to 1, means it is 0. When b equals to 1, 1 bar is 0, يبقى 0, 0. Okay? يبقى 1, 0, 0, 0. Agree? This is simple Boolean algebra. Okay? Do it whatever you want, in any method you like. Okay? I just substitute here. I can actually here see 2, 1, 2, 4 mean terms. Okay? three min terms. Okay, so it is b bar. So when a equals to 0, that means 0 bar is 1. That means it is b bar. B bar is 1 1 0 0. Right. When a equals to 1 means a 1 bar means 0. This is x bar b bar. X bar b bar has only 1 here and 0 otherwise. This is another method. Okay, so I drive the column for b of t plus 1. Now I have y. Y is an or in between a bar and b. When a equals to 0, 0 bar is 1. That means 1 or anything is 1. So when a equals to 0, the equation will be simply 1. Because it is a bar or b. It's either a bar or b. Fin b. Okay, so when a equals to 1, this will be 0. Means it is b. B means 0 0 1 1. Agree? يبقى from the circuit we get the equations. From the equations we get the state table. From the state table we can drive what? We can drive the state diagram. Okay? يبقى the last component that we want to draw here is part 4 اللي هو state diagram. The state diagram for this circuit, let me just input output analysis B. Okay, I don't want to erase it, but let us think about it. State diagram is circles and arrows. How many circles? The number of circuits is 2 to the power number of pieces. How many pieces you have here? You have 2 pieces. That means 2 to the power 2 is 4. I have 4 states. I have 4 circles. Those 4 circles are the states representing the 4 values of A and B. Because A and B together representing the state. This circuit could be in a state for A and B either 0, state A, B, 0, 0 or 1, 0, 0, 1 or 1, 1. 4 states. 4 states means 4 circles in the state diagram. So the state diagram here has 1, 2, 3, and 4 circles. Those 2 circles are for A together equals to 0, 0 or 1, 0 or 0, 1 or 1, 1. يبقى 4 circles. My state diagram has 4 circles, each of them representing one combination of the outputs of the state of the flip-flops or the states. Okay, right. Now, how many arrows? Number of arrows equals 2 to the power number of external inputs. How many external inputs? We have only one external input, اللي هو مين؟ اللي هو الX. Okay, so that means I have 2 arrows going out from each state. Those 2 arrows are actually representing here by 2 rows. So for state 0, 0, I have when X is 0, when X1. Here X0, X1. Here X0, X1. Here X0, X1. Okay, each of those arrows representing state transition. If I am in state 0, 0, and the X input equals to 0, okay, what will be my next state? My next state is the combination A of t plus 1, B of t plus 1 together. If I am in 0, 0, with X at 0, I will go to 0, 1. Finish 0, 1, add 0, 1. I have an arrow going from 0, 0, 0, 1. This is for X equals to 0. Another arrow for that state when X equals to 1. When X equals to 1, I want to go to state 1, 1. The second arrow going like that. This is for X equals to 1. Are you following? Next, state 0, 1. State 0, 1. 2 arrows. When X is 0, I will go to 0, 0. This will send me back to 0, 0. When X equals to 0. If I am in state 0, 1, will x equals to 1, I will go to the other state اللي هي ال 1 0. Okay, so I will go to ال 1 0. So let us just let me just remove here to give myself a little bit of a space. This is the state table. We know that this is the state table. So I will take an arrow here going to this state. 0, 1 will go to 1 0. When x equal to here, x equals to a, x equal to 1. Type. If I am in state 1 0, 1 0 will exit 0, I will go to 1 1. I will go to 1 1. X equals to 0. Right. I am in 1 0, x sub 1. I will stay in my state. There is no change in the state. So I will have here an arrow going out and in from this state when x equals to 1. The last case for 1 1. 1 1 and x sub 0, I will go to 1 0. 1 1. Well, x sub 1 will go also to 1 0. Both of the arrows going to the 1 0. Here I have one arrow, the second arrow, and both of them going from 1 1 to 1 0 for either x equals to 0. Let me just give myself a little bit of space here. This was for 0, and this is for 0 and 1. Agree? Make sense? Are we done? The answer is no. What is missing in that state diagram? The state diagram here is missing the external output. The external output is shown here, is showing the equation, is showing the state table. This is actually the state table, but it is not still shown in the state diagram. How can I draw it in the state diagram? I have the output y. The external output اسمه ايه؟ اسمه y. Okay? Now we have to indicate that we have two types of sequential circuits that have external outputs. One circuit is called the Mealy circuit and the other is called the Moursy circuit. In order to explain this, I just want to erase this to give myself a little bit of space. Okay, so now we not in need of this anymore. We are about to finish. One thing is left for us. اللي هو مين؟ External output representation on the circuits or on the state diagram. We have two types of circuits. We have here two types of circuits. أول واحدة اسمها الميلي circuit. طيب. Mealy circuit means that the external output is attached to the external. In the Mealy, the external output attached to an external input. The other type of circuit is called Moursy. The Moursy circuit, the external output is attached to the states. We have two types of circuit. We have a Mealy circuit and we have a Moursy circuit. طيب, how do I know that the circuit is Mealy or Moursy? The external output is attached to the states or attached to the external input. You can identify that from any of the three things, which will affect how you will draw the Y here in the state diagram. If you have, so in the circuit, you can identify whether it is Mealy or Moursy. If Y has a direct path through logic gates only to the external input, that means it is Mealy. Let's review that. Take a path retrograded from Y trying to reach to X. Trying to reach to X. Can you go through a retrograded path to X without going through the physics? The answer is no. Okay? So here you are actually, you have to go through either this flip-flop or you have to go through this to reach to the X. Some students find this difficult. Don't worry. Don't worry. We will have another way to identify. If the identification of Mealy or Moursy from here is difficult, go and check simply the equation of Y. What's the equation of Y? Equation of Y, does it have X or not? So our equation of Y here does not have X. Y equals to A bar or B. Do you see X here? I cannot see X here. So that means the circuit is, if our circuit here is Moursy, not Mealy. Right. Another way to identify. Go into the table and see if changing the external input change also the external output or not. Let's go and see. Each of those pair of rows, X is changing. I have 0, 1, 0, 1, 0, 1, 0, 1. Here 0, 1. Can you change? Can you see a change of Y? No. 0, 1 and Y is 1. 0, 1 and Y is 1. 0, 0, 1 and Y is 0. 0, 1 and Y is 0. So Y is not changing by changing X for any pair of X, 0 and 1. That means the circuit is Moursy. Yeah, I can identify it's Moursy either from the circuits or from the equation or from the table. Right. If I learned that the circuit is Moursy, as we indicated, it is Moursy. If our circuit here is Moursy, how can I draw the external output? I draw it as Moursy. The external output is attached to the state. That means I have to draw it inside the circles with the state. So I will put a slash and I will put the value of Y. Put slash and put the value of Y. So if I am in state 0, 0, what is the value of Y? It has only one value. From the table, it has only the value 1. Slash 1. Right. If I am in state 0, 1, what's the value of Y? Again, it is 1. If I am in state 1, 0, what's the value of Y? It is 0. If I am in state 1, 1, what's the value of Y? It is 1. And the circuit is Moursy. Agree? Easy, simple. Now, so what about Mealy? Okay. Can we take an example for Mealy? Let us a little bit modify this example and add a Mealy component. Okay. So I will just simply remove this for the sake of giving me a little bit of space. I will add one extra external output to demonstrate to you how the Mealy will look like. Right. Follow me in this. Can you see the output Z? Can you see this output Z? So I added here for my problem another external output and I call it Z. Can I add Z to all of my analysis? The answer is yes. Z is simply an AND between this branch is coming from X bar and ANDed with this branch which is coming from from LB bar. This is Z. Okay. Now, is the circuit mealy or Moursy? The circuit is mealy, not Moursy. Why? Because I have Z mealy. Z really mealy? Yeah. Take a branch Z. By the way, the flow of signal is coming like this. Okay? Flow of signal is coming like this. So, if you take a branch retrograded, can I go reach from Z to X without going through the flip-flops? The answer is yes. That means it is mealy. Difficult? Forget about the circuit. Go to the equation. Equation for Z. Does it contain X or not? Yes, it contains X. Yet the circuit is mealy. Okay? Can I identify that even from the table? So can we add Z here to our external output on the table? The answer is yes. This is Z. Can I drive the equation for Z, the TT for Z? Can I put Z on the table? Yes, you can. So actually, let's write Z in another color for clear. This is Z. Call this Z. We have here Z. The circuit is, due to Z, the circuit is mealy, not Moursy anymore. Okay? So I cannot call it Moursy because I added Z. If you have any one external output mealy, means the circuit is mealy. Okay? All right. Can I put Z on, this is the equation, can I put it here? Yeah, it is X bar B bar. X bar B bar means, X bar B bar means 1 here, 0, 0, 0, and 1 here, 0, 0, 0. If you don't believe me, just substitute. Okay? Okay? When I have both 0 and 0, I have this evaluated as 1. 0 and 0 evaluated as 1. Otherwise, it evaluated as 0. Now, can I conclude that this is mealy from the table? The answer is yes. Now, go to the state 0, 0. Do you have one value of Z or two values? You have two values of Z. So Z here is not following the state. It's changing by changing X. X01, Z10. Okay? If you have at least one occurrence of this on the table, that means the output is mealy and the circuit is mealy. Right. By the way, this is also repeated here. It happens twice. Here also, Z10 and X01. That means it is mealy circuit. Right. How can I draw the output if it is mealy? If the output is mealy, means that Z is attached to X. Means it's attached to X, so I have to attach it to X on the state diagram. Here I am in state 0, 0 and X is 0. Z هتبقى ب1. يبقى لما الX ب0 I have to put slash and put the value of Z. يبقى X slash Z equals to 0 slash Z بكام؟ ب1. اوكي؟ الX ب0 الY الX ب0 الZ ب1. طيب I am 0 0 والX ب1 المفروض تبقى ب0. يبقى the other row here I have Z equals to 0. Next, for this 0 1. 0 1 is Z almost ب0. يبقى the two arrows going out from here I have Z 0 and I have Z 0. طيب 1 0 1 0 again x0 z1. For this x0 is z1, x1 is z0 for 1 0. طيب 1 1 1 1 both are z equals to كام؟ equals to 0. يبقى slash 0 slash 0. So now I have a Mealy state diagram and the Mealy circuit, and everything is Mealy. This is the most comprehensive example for the analysis for sequential circuits containing more than one flip-flop, containing external outputs, Mealy and Mori. And now we are ready to go to the next step, which is the design for synchronous sequential circuits. In the next lecture, lecture number 26, we will learn, we have two lectures for the design, 26 and 27, we will learn the design of synchronous sequential circuits. Okay, and then 27, 26, 27 for the design, 28 for the counters, 29 for the registers, and the last lecture will be for the BCD representations. Okay, and we will finish the material. In the design, we will start here. Start by building the state diagram for the problem. From the state diagram, we will be able to get the state table. We will go retrograde. From the state table, we can derive the state equations. And from the equations, we can draw the circuit so to design the circuit. See you in the lecture number 26 in the sequential circuit analysis, synchronous sequential circuit design.